So we have the Basel problem, which says that the sum of all inverse squares sums to pi squared over 6, and I've seen quite a lot of different proofs for this one, but I'd like to share what I think is, well, the simplest proof that I know of. And it's simple in the sense that it's very short if you know the couple of requirements. And in terms of intuitiveness, I would say it's completely unintuitive. So that's a huge minus for them. But I still like it quite a lot because you can basically just fit it into one line. So it goes like this. First of all, we start with an integral from 0 to pi over 2 of just x dx. And this very obviously results in pi squared over 8. And you might ask, okay, what's the point of that? Got a pi squared term, but I have no way to associate it with this. Well, here's where the unintuitiveness comes from. We replace this x with sine inverse of sine of x. Yeah, this is perfectly valid in this interval. These are bijective, so that's perfectly fine. And now, we now expand sine inverse of x as its power series. Now, so I have this one requirement. You should know that sine inverse of x has a power series expansion given by the sum as n goes from 0 to infinity of 2n minus 1 double factorial over 2n double factorial times x to the 2n plus 1 over 2n plus 1. This is with a asterisk. The zeroth coefficient for this has to be 1. Do not use the formula. The formula is valid for n1 and greater. The zero term has to be 1 because sine inverse of x for small values of x has to be x. So just replacing sine inverse here, the power series, and integrating term by term. Just taking out everything that doesn't have x outside the integral. We're left with this integral. Integral from 0 to pi over 2 of sine of x to the 2n plus 1 power. Oh yeah, I forgot to explain the double factorials. In case you don't know, double factorials just means instead of where we had factorials that we multiplied by numbers smaller than that number until we reach 1, here we do the same but reduce it by 2 until we reach 1 or 2, depending if the number is odd or even. And now I need a second requirement. Is that we can solve this integral exactly. So this integral of sine of x to the 2n plus 1 power is indeed just 2n double factorial over 2n plus 1 double factorial. And if we have this, placing this here, we have 2n double factorials cancel. We got 2n minus 1 double factorial over 2n plus 1 double factorial. And a 1 over 2n plus 1. And notice this is also 2n plus 1, simply because of the recurrence relationship. A double factorial is the same as, well, that same number times the double factorial of the input that is 2 less. So 2n plus 1 times 2n minus 1 double factorial. And this gives us the sum, as n goes from 0 to infinity, 1 over 2n plus 1 squared, which is all the odd even squares. And we're basically done. Very basic algebra can be used to just to get from here to here, but we got the main result. I'll show the little trick used to get this at the very end. Now I'll just quickly prove the prerequisites. So the simplest way to show that this is indeed the power series for inverse sine is to construct its Taylor series. Or not exactly its Taylor series. We know that sine of inverse of x can be computed as an integral from 0 to x of 1 over 1 minus 1 over the square root of 1 minus t squared. So instead we should construct the Taylor series for this function, or not even this function. Let's construct it for 1 over 1 over the square root of 1 plus t, and then just replace t with minus t squared. So recall that the Taylor series is written as sum as n goes from 0 to infinity of the nth derivative of the function evaluated 0. I'm just gonna center this at 0, or n factorial times t to the n. So let's look at the function and its derivative values at 0, and we'll very quickly see what's the pattern. So at 0, this is 1. Its first derivative would be using the power rule, just minus 1 over t, 1 plus t to the minus 3 over 2 power. Applying the chain rule here changes nothing. This derivative value at 0 is minus 1 over 2. And we take another derivative, we get now 1 times 3 over 2 times 2. The power is now minus 5 over 2. Evaluate 0, this is 1 times 3 over 2 times 2. And now I think you can kind of figure out the rest. The next value will be 1 times 3 times 5 over 2 times 2 times 2, and so forth. Let's see, the nth derivative of 0 would be, if we had 3 and this is 5, this would be 2 times 3 minus 1, so the top would be 2 times n minus 1 double factorial, and there's how many 2's in the denominator? However many derivatives we have, so it would be 2 to the n. And now the coefficient would be f(n) 0 over n factorial, so this over n factorial. And now we use a little property that for even double factorials, so for example taking 8 double factorial, this would be 8 times 6 times 4 times 2. We can factor out a 2 out of each of these factors, get a 2 to the 4 times 4 factorial. So 2n double factorial can be written as 2 to the n times n regular factorial, which is exactly this denominator, so this would be 2n minus 1 double factorial over 2n double factorial, which is exactly what we wanted. Now replacing t with minus t squared would actually remove the minus that I forgot here. Yeah, I forgot that, we have a negative that appears on every other term here, but replacing with the t with minus t squared would would remove that, and integrating t to the 2n from 0 to x would be x to the 2n plus 1 over 2n plus 1, which is just the formula that we wanted. So I consider this done. Yeah, nothing but professionalism here. Trust me, I have a whiteboard. So this integral, this also has many different ways of solving it, and I think I found one that's quite easy. So first of all, I will denote this as I 2n plus 1, as in the index matches the power here. Notice first of all I1 is just 1 of sine of x from 0 to pi over 2. Pretty obvious. And now we want to create a recurrence relationship, one that will end up using double factorials. So first of all, we do this one trick. We take a factor of sine squared from this and write it down separately. And now write the sine squared as 1 minus cosine squared. And separate this into two integrals. First of all, this first integral, which is I of 2n minus 1. And this other integral, which we will actually not even need to solve, is sine of x to the 2n minus 1 times cosine of x squared dx. And I'm going to just denote this as j. And now we do another recurrence and now we create another recurrence relationship in a different way. So now we only factor a sine term instead of sine squared. And we integrate by parts. So we choose to differentiate sine of x to the 2n and integrate sine of x. Integral of sine of x is just minus cosine of x. The derivative of sine of x to the 2n is chain rule 2n times sine of x, 2n minus 1 times cosine of x. So by parts we have minus sine of x to the 2n times cosine of x, evaluated from 0 to pi over 2, which by the way is 0 because cosine of pi over 2 is 0 and sine of 0 is 0. And we get an integral of 2n times, 2n times sine of x to the 2n minus 1 times cosine of x squared. And this is now the same integral I denoted by j. So we have 2nj. And these two equations are enough to get this. So to solve this, I'm just going to express j as I have 2n plus 1 over 2n. So this would give me 2n minus 1 minus 2n plus 1 over 2n. Now I bring this to the left side and factor out 2n plus 1. Be 2n plus 1 times 1 plus 1 plus 1 over 2n equals I have 2n minus 1, and this is with common denominators would be 2n plus 1 over 2n, or I have 2n plus 1 is I have 2n minus 1 times 2n over 2n plus 1. So combining this with I1 being equal to 1, we're basically done. Since now we have, say, I7 is I5 times 6 over 7, putting n equals 2 would give I5 equals I3 times 4 over 5, and I3 with n equals 1 would be I1 times 2 over 3. Now chain these together, we get I7 is 6 over 7 times 4 over 5, or times 2 over 3, which is 6 times 4 times 2 over 7 times 5 times 3, which is 6 double factorial over 7 double factorial. So yeah, this basically, for any general n, we show that I2n plus 1 is 2n double factorial over 2n plus 1 double factorial. And lastly, I want to show you how we can get the sum of all inverse squares from the sum of all odd inverse squares. So let's just denote S as the sum of all inverse squares, and we subtract this sum that we got from before. I'll make it a bit more obvious by writing it like this. Subtracting all odd terms, we only have all even terms remaining, so that would be 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared, so forth, and we can factor 1 over 2 squared from all of these, and we have 1 plus 1 over 2 squared plus 1 over 3 squared, which is just some s again, so this is 1 over 4s, and now all that remains is to express s from this. So we have s minus pi squared over 8 equals 1 over 4s, or 3/4 s is pi squared over 8, or s is 4 over 3 times pi squared over 8, which is indeed just pi squared over 6, and yeah, we're done.